Hello, welcome to the Virtual Beach video tutorial series. These tutorials were created with the support of both the University of Wisconsin Sea Grant Institute and the Great Lakes Observing System. My name is Sonia and I will be leading these tutorials. At the website virtualbeach.org you will find all of the video tutorials, many helpful hints, and links to data sources. The 3.0.6 version of the Virtual Beach software will be used in these tutorials. Download and install the Virtual Beach program before proceeding. A link to the download page can be found at the top of virtualbeach.org. The link takes you to the United States Environmental Protection Agency website where you can download the software. These tutorials are intended to walk you through the Virtual Beach software that was created by the US EPA. Virtual Beach is a predictive modeling program that can assist managers in making advisory decisions at fresh and saltwater beaches. With this software, beach managers can create models to predict bacteria levels at a beach. This tutorial, Data Preparation for an MLR Model, walks you through the fourth of 6 modules demonstrating how to use the Virtual Beach software. If you have not completed the first tutorial, please do so now. You need to use the project file created in the first module, Beach Orientation, for this current tutorial. If you would like to proceed without determining the orientation of a beach on your own, you can download the demonstration project file from the Virtual Beach Step-by-Step Training Modules page. The demonstration file is contained in the zip file found in the first section. You will need to also download the data file VB Training Data MLR to your computer. A link to this file is under the fourth section, Preparing Data to Create an MLR Model. Save the file where you can easily locate it when in the Virtual Beach program. Detailed directions for this module are available at virtualbeach.org in the Training section. Under the subheading Virtual Beach Step-by-Step Training Modules, select the Data Preparation MLR PDF. Either open the PDF on your computer or print it so that you can follow along with these instructions. By the end of this module, you should be able to import and clean up model data for your beach, process directional data for wind, currents, and waves, combine 2 or more predictive variables, and transform variables and explore potential relationships. Preview the data you will be importing into Virtual Beach by opening Microsoft Excel. Open the file VB Training Data MLR. The worksheet MLR Model Building Data 2009-15 contains the data used to create the model in this tutorial. Note that column B is always the response variable E. coli in this example. All data to the right are potential explanatory variables. Definitions and sources for each potential explanatory variable can be found in the key worksheet. The worksheet MLR Validation Data 2016 will be used in the next module to validate the model you create in this tutorial. Close the Excel file before returning to Virtual Beach. Data cannot be imported from an open Excel file. When you create a model in the future, be sure to save your data as an XLS file. A plugin for Virtual Beach 3 is available for importing XLSX files, but there are still bugs to be worked out. Now, open the Virtual Beach program. Next, open the file you saved during the previous module, Beach Orientation. Then click on the Location tab. Note, sometimes the beach orientation appears as 180 instead of 21.15. The water is marked correctly, but the number is wrong. If you click Remove Water Marker, then click on the water in front of the beach area, and finally click Add Water Marker, the correct beach orientation number appears in the box. Now click the Global Data Sheet tab. Click the Import Data icon. Select the Excel file VB Training Data MLR and click Open. In this example, there is more than one worksheet in the Excel file, so you must choose which one to import. Select the worksheet MLR Model Building Data 2009-15. Click OK. The data table opens and Virtual Beach automatically highlights the second column of the datasheet as the response variable. E. coli is highlighted here. The response variable is indicated in the left-hand panel, along with column count, row count, and other descriptions of the data. Virtual Beach will not build a model if any cells are blank. Models can only be built when every cell contains a number. Click the Validate Data icon to check your dataset. In the pop-up window, click Scan. In this tutorial, the CloudCov qual column is flagged because the values are text or non-numeric. Click the radio button next to Delete column. Under Take Action Within, make sure only this column is selected. Click Take Action. The next column, Trib6, will be flagged. The variable is numeric, but some cells are empty. Do not remove the entire column. Instead, click the radio button for Delete Row. Select Entire Column and click Take Action. All rows with empty cells in this column are deleted. Repeat scanning until a notice appears at the bottom of the pop-up window stating No anomalous data values found. Then click the Return button. Now it is time to process wind and current data. Click the Compute AO icon. In the pop-up window, under Wind Data, click the pull-down arrow next to Speed and select WSPD. For direction, select WDIR. Repeat for current data, selecting CSPD and CDIR. Again, repeat for wave data, selecting WVHT and WVDIR. The beach angle is then automatically calculated. Click OK. If you scroll to the far right end of the table, 6 new columns will have been added to the end of the global data sheet. Wind A comp, along shore wind speed, Wind O comp, toward shore wind speed, Current A comp, along shore current speed, Current O comp, toward shore current speed, Wave A comp, along shore wave height, Wave O comp, onshore wave height. Note that the unprocessed wind, current, and wave data columns are now inactive as indicated by being shown in red text. Now you can combine 2 or more predictive variables. In situations where predictive variables are themselves correlated, meaning they interact with one another in terms of how they influence water quality, it may be beneficial to combine them into a single interaction term by multiplying them together. By combining 2 variables, a better prediction of water quality may be found than if the independent variables are used individually. First, create an interaction term by multiplying 2 variables together. Click the Manipulate icon. In the pop-up window, Control-select Wave Height, Feet, and Gulls. Click the right arrow button. Click the radio button next to Product. Click the Add button. This creates an interaction term that may describe more accurately how wave height influences the number of gulls on the beach. Shift-select Wave Height, Feet, and Gulls, then click the left arrow button to move them back to the main list. Next, create an expression of combined categories. Some variables are either yes or no. The 0 is no and the 1 is yes. In situations where binary variables represent successive categories of some qualitative variable like visually observed water clarity, it may be useful to combine them into a single binary variable by summing them. The resulting variable will have a value of 1 when either of the 2 conditions is present. This can be especially helpful when there is little functional distinction between the categories, or few cases in which one of these conditions is ever observed. In this example, the difference between turbid and opaque water is not very distinct. If the water is turbid, it was probably also opaque. Combine turbid and opaque using the Sum Radio button. This combined expression creates a variable where a visual observation of either turbid or opaque water receives a value of 1. Shift-select turbid and opaque. Click the left arrow button to move them back to the main list. Finally, you can create an expression that describes a change in flow variable. In situations where continuous stream flow data are pre-processed over different time frames, subtracting one temporal snapshot from another can create proxy variables for changes in flow. The difference between 24-hour maximum and minimum flow rates indicates whether recent tributary discharge has been consistent or very different after a flash flood event. Shift-select both the trib max 24 and trib min 24 columns. Then add them to the right arrow button using the diff radio button. Add this equation also. This approximates whether and to what extent the previous 24 hours of tributary discharge has been constant or varied. Other manipulations can be added as needed. Click OK when complete. Transforming variables. Right-click on the E. coli column header and select Transform, log 10. To build a usable nowcast model, bacteria counts must be transformed. Log 10 is a common transformation for microbial concentrations. In addition to transforming the response variable, transforming explanatory variables can significantly improve model fit. Click the Transform icon. Check all options except polynomial and type 0.6666 next to general exponent. Click Go. As of July 2017, the polynomial transformation causes problems in the Virtual Beach program. Future updates should address this issue. A pop-up window will open listing all of the optional transformations for each explanatory variable. Those in black represent the transformation with the best correlation, Pearson's coefficient, with the response variable of log E. coli. Right-click in any cell to the left of a variable so that you can view scatter plots of all the transformations of that variable versus log E. coli. For example, right-click to the left of the variable wave height, feet. Note that in this case, the best transformation, in terms of Pearson's R, is square transformation. The scatter plot confirms this selection. Close the window to return to the list of transformation options. If you decide to select an alternative best transformation for a given variable, simply click on that row. When you are finished, click OK. New columns are added if the newly transformed variable had a better fit than the untransformed original variable. The new columns here are square of water temp, quadroot of wave height, and quadroot of air temp. The original columns are now disabled as indicated by red text. Disabled columns will not be used in the module. Now save your project file. You can now move to the next module, Building an MLR Model.